All right. Hey everyone. Welcome back. So the purpose of this video is just to a lot of it'll be a bit of a recap of what we talked about in class. And so we're still talking about z-scores and why they're kind of useful to get two different measurements to be on the same scale. The example we did was the SAT and ACT, which are standardized tests that you typically, though they seem to be phasing out a little bit, typically take them to as a kind of prereq to get into a college. And so we're picking up, now I'm on the top of page 5 of our note packet. And so remember the formula for a z-score is we would just take the observation, subtract the mean, and then divide by the standard deviation. Because we're doing that, what we're actually doing is recentering it, since we're subtracting the mean, so that it's this z distribution is going to be centered at 0. And then since we're dividing it by the standard deviation, that means that the spread of a z distribution is always going to be 1. And so our z distribution graph is always going to be centered at 0, and then its tick marks are always going to be by 1. So I think it's a little bit easier to see the centering. If you subtract the mean, then if the mean was 700 and then you subtract 700, then now it's going to be centered at 0. So let's kind of recap and do another example with this ACT-SAT data. And so we've got two more students. We've got Enrique and we've got Michelle. Enrique just took the SAT and Michelle just took the ACT. And so we want to compare these two students to see who did better. And so remember from before that the mean SAT score was 1100, the standard deviation was 200, and so we could figure out Enrique's z-score. And so he scored 1050, and then it's kind of just easy algebra to figure out that Enrique's z-score is negative 0.25. So we could do the same exact thing for Michelle. So remember the mean ACT score was 21 and the standard deviation was 6. And so Michelle's z-score is going to be 19 minus 21 divided by 6, or that would be negative 0.3333333. All right, and so who performed better? Well, in this case, Enrique, just barely. So we could say Enrique performed better because his z-score is larger. And in this context, larger is better. And so you could think of something like maybe a running time for a race. In that context, then a smaller z-score would be better because smaller z-score would indicate that you ran the race faster. So it is context dependent. So we could also interpret Enrique's z-score like we did before. And it's negative now, indicating that he scored below the mean, which we could see directly from the data. So he got 1050, the mean is 1100. So our interpretation is just something like Enrique scored 0.25 standard deviations below the mean. or if I want to put this more in context, below the mean SAT score. Okay, so we also talked a little bit about percentiles in class, and we kind of wrote the definition. But again, if we kind of think about this, I think a common example that many of us would have seen percentiles in is in standardized testing. So even depending on the state you went to school in, you might have taken various standardized tests, even in grade school, middle school, high school, and you would usually get results back that would be like, okay, for literature, for English, you scored in the 72nd percentile. And all that means is that you scored better than 72% of the people that took that test. In other words, the proportion of cases lower than the value that you scored is 0.72. And so we can figure out these percentiles from the normal distribution, but we need some extra technology. And so before we get to that, we'll be using a stat key. But before we actually use stat key, let's go ahead and do a couple drawings just to get some intuition about what these percentiles are going to look like. And so we could start with Anne, who we had in the last video. So remember, she scored a 1300 on her SAT. And so let's draw our normal distribution curve. That's just going to be a little sketch. And so remember, the standard deviation was 200, so I'm making my tick marks by 200. Anne scored right here. And so Anne's percentile is going to be the percent of area that's shaded in this graph, because percentile is the proportion of cases lower than the value of interest. And so I'm going to guess, based on my graph, that Anne is about maybe the 80th percentile, because that area looks to be about 80% of the entire area that's under the curve. But we'll use stat key to figure out her exact percentile in a second, so I'm going to put a question mark there, and we'll come back to that in the next video. We could also look at Michelle and take a guess for her percentile. Oh my god, that looks terrible. Okay, hold on. That is too bad to be useful. All right, and so again, I'm going to draw my tick marks. Michelle also took the SAT, and she scored... Oh, Michelle took the ACT. That's a double, my bad. So ACT, mean of 21, standard deviation of 6. Michelle scored a 19, so she's about here. And I'm going to shade the area that represents her percentile. I'm just going to guess that that area is about 30% of the area of the entire graph. So I'm going to write 30th percentile. But we need stat key to actually, or some other form of technology to really figure that out. Calculus is obviously not a prereq for this course, but just to connect it, if you have taken calculus or you are taking calculus now, this normal distribution, you can't actually integrate it. And so that's why you need some extra technology. Again, that's just an aside. You would have actually had to take probably Calc 2 to talk about integration. But if you haven't taken Calc, then just ignore that last 30 seconds. Okay, so where we're headed next is, in the next video, we won't be using the .cam. We're just going to use the computer, and we'll talk about stat key and a little bit about how to use it.